In this video, we're going to talk about the idea of the center of a group as well as centralizers of specific elements of groups. All right, so this is a topic that is going to become useful for us a little bit later in the course, but we're going to introduce it here because it's a nice example, or a couple of nice examples of subgroups of a given group. So again, let's let G be a group. And we'll go ahead and make this a definition here. So this is definition. Let G be a group. The center of G usually denoted Z of G is the set of all elements of G that commute with every element of G. And we'll go ahead and write that formally like this. Z of G, the center of G, is equal to the set of all G, elements of G, such that GH equals HG for every H in G. Okay, so again, that sentence is just saying it's the set of all group elements such that that group element commutes with H for every H in G. Okay, so if that happens, then it's not the H that belongs to this set, it's the G. It's the G that commutes with everything. Okay, so that's the center of G. And I claim that that's a subgroup, but I'm going to hold off for just a minute and make one other definition here. So one more definition, let G be a group. And let's let A be an element of G. The centralizer of A in G. And here I'm going to depart a little bit from the book's notation for this because I want to preserve a couple of things in the notation. So we're going to call this C subscript G parentheses A. The centralizer of A and G is the set of all elements of G that commute specifically with A. Okay, so those elements might commute with other things, but we're looking at the set of all elements that commute with A. So we write this formally as C sub G of A equals the set of all G belonging to G, such that GA equals AG, and that's it, because at this point A is fixed, so I don't need to say for every A or for some A. A is whatever's in these parentheses here, so this is fully defined. I said this is a bit of a departure from Gallien's notation. I think that Gallien uses this notation, just C of A, without the subscript G. I like the subscript G because at some point we may talk later in the course about centralizers of a given element either within G or within some subgroup of G. And those are going to look different because here we're taking all of the elements of G that commute with A. And if we're looking at a subgroup and focusing on that subgroup H, for example, we might be looking at just elements of H that commute with A. So I'd rather have the group there just so that we know what the ambient space is. Okay, so I claim that this is a subgroup of G, and also that this is a subgroup of G. And I think I'm going to prove one of those here and then leave the other for you to think about. And I think I will do this for the center of G. I'll prove that the center of G is a subgroup of G. So since we're going to focus on the center, let's move this down and let's see if we can prove it. All right, let's pick a new color. There we go. Okay, so this is the proof that the center of G is a subgroup of G. Remember that that less than or equal to notation means subgroup. All right, so here's the proof. How do I want to approach this? I think I'm going to try using, I think I'll try using the two-step subgroup test just for variety's sake. I think I could probably use the one-step, but we'll use the two-step subgroup test, which means we need to prove, actually we have to prove three things. I think it's funny they call it two-step because really we need three things. We need to prove non-empty, that the center is non-empty, which takes a bit of thinking, like how do we know that there's an element of G that commutes with everything? But we actually do know that there is one. So we need to prove that the center of G is non-empty, it's closed under the group operation, and that it contains the inverse of each element in the set. So if something's in the center, its inverse also is in the center. Okay, so first of all, I hope that while I was finishing that previous sentence, how do we know that there is an element of the center of G? How do we know it contains anything at all? What is there in G that we know commutes with everything? Well, there's the identity. We know for every H in G, the identity times H equals H times the identity, because both of those are equal to H. So the identity belongs to the center of G. There's no question about that. It doesn't depend on what group we're talking about. So the center of G, at least it's not empty. So that's good. Okay, what about closure? So to prove closure, let's suppose A and B both belong to the center of G. So we will prove that AB also belongs to the center of G. And to prove that, now again, this is an exercise in using the definition of a set down here. Here, this is what it means to be in the center of G. And we're going to have to unpack that to interpret what it means for A and B to be in there. And then we're going to have to repack that so that we can show that AB belongs to that set. So to show that, we need to show that AB commutes with every element of G. All right, so what do we know? Since A belongs to the center of G, AH equals HA, aha, see, aha. AH equals HA for every H in G. Sorry about that. Okay, also since B belongs to the center of G, BH equals HB for every H in G. Okay, no funny pun to be had there, I guess. So what do we know? So if H is in G, and I need to prove this for every H, I need to prove that AB will commute with H. We have AB H equals A times BH. I'm just being super careful about the associative property so we can fully appreciate the role that plays here. And then we know that because I can commute B with H, because B's in the center, that's equal to A times HB. Hooray. And then I can reassociate and get A and H together. And then because A equals ha, because A is in the center, I know that that's true. So then I can reassociate and get H on the left side of AB. By the way, when writing one of these, I'm actually writing this very compactly because I'm on a whiteboard here, but a lot of the time I like to see reasons for things. So this is because B is in the center of G, and then this step here works because A is in the center of G. Okay, I might actually, if I were doing this on paper, I'd probably write each of these on a separate line, even though that's a waste of a lot of lines, I think, and then write these reasons out to the side. That's probably a more stylistically, I don't know, conventional way of writing it. Okay, but anyway, so AB commutes with each H in the group because I just let H be arbitrary here. I didn't put any restriction on it. Thus, AB belongs to the center of G, and that's great. So that means this set is closed under the group operation. So that's terrific. But what about inverses? I still need to prove that inverses belong to the center, and I'm out of space. So I'm going to zoom out and create some more space for myself over here. All right, so let's try that then. Okay, so now, suppose A belongs to the center of G. We'll prove that A inverse also belongs to the center of G. Now this one's a little bit trickier because I'm going to have to pull something out of my hat here. So again, let's let H belong to G. Okay, because I want to prove that A inverse commutes with every H. We'll show that A inverse H equals H A inverse. That would mean that A inverse commutes with H. Okay, now just thinking out loud here, I'm going to do something that's predicated on this, which is not, strictly speaking, legal, But I'm going to do a little bit of algebra here that will map out for me how I might reach this point. So at this point, I'm going to jokingly say that I'm engaged in a proof by wishful thinking, which I take to mean that I am taking this as an assumption, which I am really not allowed to do. That's what I'm trying to prove. But I'm just going to map out, if that were true, what else would be true? Because I think I will be able to reverse the reasoning, so I'm reasoning from known premises to the thing I want to prove. Okay, so here's what a proof by wishful thinking might look like here. I want to show that A inverse commutes with H. So I want to show that this statement here is true, that A inverse H equals H A inverse. Now, one thing I might try is I might just multiply everything on the left by A, so as to get rid of this A inverse, because I actually know a lot more about A than I know about A inverse. I know that A commutes with everything. But the thing is, here, I have to be really careful. If I'm multiplying by A on both sides, I need to multiply it on the left consistently, because I know that these are the same group elements, which means that A times each of these is the same, but that's not necessarily the same if I multiply this on the left by H and then this on the right by H. That doesn't, I may not get the same result if I do that. So on the left side, I just have H because A inverse is the identity. And on the right side, I have A inverse. And now I'm going to also multiply on the right by A on both sides. And if I do that, then I get the identity here, which means I'm left with just HA equals AH, which is something that I know to be true because A belongs to the center. So now I'm just going to use a little strategy I call RATS. Reverse all the steps, while making very sure to verify that I can actually reverse all of these logical steps here. So here's how that's going to go. I'm going to start with something I know. So I'm going to continue the proof over here. There we go. All right, so we're going to show that A inverse H equals HA inverse. So now I'm going to say something which appears to have no immediate logical connection to the thing I want to show. This is what happens a lot of the time when you do proof by wishful thinking, is you get this first step, which in the actual write-up of the proof looks like it's kind of out of nowhere, but it's because of all this work that you did here. So I'm going to start by writing that down. We know HA equals AH because A belongs to the center of G. This is something we know. So A commutes with H. Now, rather than just reversing all of these steps, which I think kind of results in some unmotivated looking steps, like all of a sudden introducing an A inverse A, I'm going to use sort of the idea that came out of this, which is we can get from here to here by introducing some inverses, by multiplying on both sides by inverses of A. So that's what I'm going to do. So multiplying on the left by A inverse on both sides yields this. A inverse HA equals A inverse AH. And now I have the identity here, so I can rewrite this as A inverse HA equals 1H, since A inverse is the inverse of A. So A inverse HA equals H. But now I would also like to have an inverse on the right side, so I'm going to multiply both sides on the right by A inverse. So I'm going to write that. So then I get A inverse HA A inverse equals H A inverse. And now since I have A inverse here, that's also the identity. So now I think I just have A inverse H equals H A inverse. And that's what I wanted to show. So A inverse commutes with H. And that's true for every H and G, because again, I just let H be anything in G. I didn't put any restrictions on it here when I set this up. So this means that the center contains the inverse of every element in the set. So let's zoom out a bit and we'll wrap this up. Okay, so the center contains the inverse of each of its elements. So now I know it's not empty, it's closed under the group operation, and it has inverses. So by the two-step subgroup test, Z of G, the center of G, is indeed a subgroup of G. Yay. So that's the proof. And you'll see that the proof that the centralizer of an element is a subgroup uses a lot of the same reasoning.